Hello students. So from today onwards we are going to revise chapter 2, 5, 6 and chapter number 10 for the first terminal exam. Okay. Now for the first terminal exam you have been given question bank. So please go through the question bank. If there is doubt in question bank, please let me know. Okay. So from today we are going to have a revision session. So today we are going to discuss chapter number 2. Okay. So chapter number 2 is solutions. So in today's video we will discuss what are the important topics and what should be the appropriate answer for the given question. Okay. So the chapter solution starts with definition. What is solution? So solution is a homogeneous mixture, right? Which comprises either two components or more than two components. Okay. Then there is classification of solution based on physical state. So there are three classes of solutions: solid solution, liquid solution and gaseous solution. Then chapter deals with different types of concentrations. Okay. So we'll revise the formulas. First is molarity. So molarity is mole per liter, right? We know the formula of molarity, mole per liter. So formula will be weight of solute divided by molecular weight into volume of solution. So if volume of solution is in ml, then you need to multiply it by 1000. So this is molarity, which is indicated by capital M. Then molality, which is indicated by small m. So molality is weight of solute divided by molecular weight into weight of solvent, which is in gram. Then you need to multiply it with 1000. Okay. Next formula is percentage weight by weight. So percentage means mass of component divided by total mass, and this is percentage, so you need to multiply it with 100. Same way, the formula of mass percentage weight by volume is mass or weight of component upon total volume of solution, total mass of solution or total. Then percentage volume by volume is equal to volume of particular component upon total volume into 100. Okay. Then ppm. ppm is parts per million. So part of any component, the one part of any component divided by total parts of component, total parts of solution into 10⁶. So mole fraction is equal to moles of any component, mole of component. So I am writing in short form, mole of component divided by total mole of components divided by total mole. Okay. So mole of particular solute or solvent divided by total mole. Total means moles of solute plus moles of solvent. Okay.
For example, in a solution of salt in water, salt is a non-volatile solute and does not contribute to the total vapor pressure of the solution. Thus, the vapor pressure of the solution will be the vapor pressure due to the solvent only. That is, P total is equal to P1 or P total is equal to X1 P1 naught, where P1 naught is the vapor pressure of the pure solvent at a particular temperature and X1 is the mole fraction of the solvent 1. On the basis of Raoult's law, the liquid solutions can be classified into ideal and non-ideal solutions. Let us first discuss the ideal solutions. A solution that obeys Raoult's law over the entire range of concentration is said to be an ideal solution. For an ideal solution, the enthalpy of mixing and the volume of mixing of the pure components are 0. This implies that no heat is evolved or absorbed, and also there is no change in volume on mixing of the two components. For example, if 50 ml of hexane is mixed with 50 ml of heptane, the volume of the solution obtained is exactly 100 ml, and no heat is evolved or absorbed in the process. At the molecular level, the ideal behavior can be explained in terms of the intermolecular attractive interactions between the two components. If A and B are two components, then in an ideal solution, the magnitude of A-B interactions will be same as the magnitude of AA and BB interactions. However, in real life, there is actually no such thing as an ideal mixture, but some liquid mixtures get fairly close to being ideal. These are mixtures of two very closely similar substances. Some common examples of mixtures that show nearly ideal behavior are hexane and heptane, benzene and methylbenzene, chloroethane and bromoethane. Since ideal solutions obey Raoult's law, they show the graphical behavior as shown here. Let us now discuss non-ideal solutions. Solutions that do not obey Raoult's law over the entire range of concentration are said to be non-ideal solutions. Non-ideal mixtures produce curves rather than straight lines as shown here. The dotted straight lines represent the ideal behavior and the curved lines represent the deviations from the ideal behavior. The reasons for the deviation are the intermolecular interactions at the molecular level. For a non-ideal solution, the magnitude of AB interactions is not same as the magnitude of AA and BB interactions. Also, delta H mixing is not equal to 0 and delta V mixing is not equal to 0 for such solutions. If the magnitude of AB interactions is weaker than the magnitude of AA or BB interactions, then this implies that such solutions have a higher tendency to escape in the vapor phase and will show a higher vapor pressure. Such solutions are said to exhibit positive deviation from Raoult's law. The total vapor pressure of such a solution is greater than the vapor pressure corresponding to the ideal solution of the same composition. For example, a mixture of ethanol and cyclohexane shows positive deviations from the Raoult's law. Ethanol exists in highly associated form due to hydrogen bonding. On addition of cyclohexane, its molecules get in between and there is a considerable reduction in ethanol-ethanol hydrogen bonding. As a result, it becomes easier for the ethanol molecules to escape into the vapor phase, and thus we see the positive deviations from the Raoult's law. For a positive deviation, delta H mixing is greater than 0 and delta V mixing is also greater than 0. Methyl alcohol and water. Carbon tetrachloride and chloroform are some other solutions that exhibit positive deviation from the Raoult's law. On the other hand, if the magnitude of AB interactions is greater than the magnitude of AA or BB interactions, the escaping tendency of A and B type of molecules decreases and the partial vapor pressure of each component decreases. This in turn results in the decrease of the total vapor pressure of the solution. Such type of solutions are said to show negative deviations from the Raoult's law. As you can see here, formation of a H bond takes place between the chloroform and the acetone molecule. This decreases the escaping tendency of the individual molecules and results in negative deviation from Raoult's law. For the solutions exhibiting negative deviations, delta H mixing and delta V mixing both are negative. A few more examples of non-ideal solutions exhibiting negative deviations are phenol aniline and chloroform diethyl ether solutions. A detailed look at the two graphs show that there are some large deviations from ideal behavior at specific compositions. These very large deviations from ideality form a special class of mixtures known as azeotropes or constant boiling mixtures. Azeotrope is thus defined as a special class of liquid mixtures that boil at a constant temperature and at a certain composition. At this condition, the mixture behaves as if it was a single component with one constant boiling point. In such cases, it is not possible to separate the individual components of the mixture by fractional distillation. Azeotropic mixtures can be further classified into two categories: minimum boiling mixture and maximum boiling mixture. Let us first discuss the minimum boiling azeotrope mixtures. When the positive deviations from ideality are sufficiently large, the mixture is said to be a minimum boiling azeotrope. As you can see from the graph, the total vapor pressure of the azeotrope is given by the maximum, represented as O in the curve. Now, as the vapor pressure is maximum at this point, it gives a minimum boiling azeotropic mixture. At this point, O, the concentration of the vapor phase, is the same as the concentration in the liquid phase and is referred to as the azeotropic concentration. Ethanol and water form a minimum boiling azeotrope at 351.15 Kelvin and at a composition of 95.4% ethanol and 4.6% water. Let us now discuss the other type of azeotropic mixtures: the maximum boiling azeotropic mixtures. When the magnitude of negative deviations from ideality is very large, the total pressure curve in such cases passes through a minimum X. As you can see in the diagram, the point X corresponds to the minimum vapor pressure, so this will result in a maximum boiling azeotropic fraction. Nitric acid and water is an example of maximum boiling azeotrope. The azeotropic composition of this mixture at 393.5 Kelvin is 68% HNO3 and 32% water. Colligative property or nature. Various relations derived for colligative properties hold good only for solutions of non-electrolytes, as there is no change in the molecular state of the solute. When a solute undergoes dissociation or association in a solution, then the number of particles of the solute in the solution increases or decreases respectively. Thus, the colligative property changes accordingly and we get abnormal results. Inorganic acids, bases, and salts undergo dissociation either completely or to some extent in an aqueous solution. For example, if 1 mole of potassium chloride, KCl, is dissolved in water, then the aqueous solution contains 1 mole of potassium ions and 1 mole of chloride ions. In such cases, the number of effective particles in the solution increases, and therefore, the observed colligative properties like osmotic pressure, elevation of boiling point, and depression of freezing point are much higher than those calculated on the basis of undissociated single molecules. Further, as molar mass is inversely proportional to the colligative property, the experimentally determined molar mass will always be lower than the true value for dissociation. For KCl, as the number of particles becomes double, the observed colligative property is double than the expected value, while the observed molar mass is half the expected value. That is, 74.5 grams divided by 2, which is equal to 37.25 grams. Similarly, there are many organic solutes that undergo association in a non-aqueous solution. That is, 2 or more molecules of the solute associate to form a bigger molecule. For example, ethanoic acid in benzene exists as a dimer due to hydrogen bonding. Thus, the number of effective molecules or particles in the solution decreases. If the association of ethanoic acid is assumed to be complete, then the observed value of the colligative property will be half, and the molecular mass would be double the expected value. When the molecular mass of a substance, as determined by studying any of the colligative properties, comes out to be different than the theoretically expected value, the substance is said to show abnormal molecular mass. In order to account for all such abnormalities, Dutch chemist J. H. van 't Hoff, in the year 1880, introduced a factor, I, known as van 't Hoff's factor, which represents the extent of association or dissociation of a solute. Quantitatively, van 't Hoff's factor I is defined as the ratio of the observed colligative property to the calculated colligative property. Thus, the expression for I can be written as I equal to the observed colligative property divided by the calculated colligative property. Now, since colligative property is inversely proportional to molar mass, I, in terms of molar mass, becomes I is equal to normal or calculated molar mass MC divided by abnormal or observed molar mass MO. Further, as the colligative property depends directly on the number of particles present in a solution, it can also be written as I is equal to total number of moles of particles after association or dissociation divided by number of moles of particles before association or dissociation. Note here that the calculated colligative property takes into account the assumption that the non-volatile solute has undergone neither association nor dissociation. The value of Van 't Hoff's factor is less than 1 if there is association of the solute in a solution, and is greater than 1 if there is dissociation of the solute in a solution. For substances that undergo neither dissociation nor association in a solution, I is always unity. If a solute undergoes 100% dissociation, then Van 't Hoff's factor is equal to the number of ions produced from one molecule of the solute. For example, the value of I is 2 for aqueous KCl. This signifies that KCl has dissociated completely into potassium and chloride ions. The value of I equal to nearly 0.5 for ethanoic acid in benzene, which signifies that nearly the entire ethanoic acid has undergone association and exists as a dimer. The modified equations for colligative properties using the Van 't Hoff's factor can therefore be written as relative lowering of the vapor pressure of solvent P1 naught minus P1 divided by P1 naught is equal to I multiplied by N2 divided by N1. Elevation of boiling point delta Tb is equal to I multiplied by Kb multiplied by M. Depression of freezing point delta Tf is equal to I multiplied by Kf multiplied by M. Lastly, the osmotic pressure of a solution pi is equal to I multiplied by N2 multiplied by R multiplied by T divided by V. The degree of association as well as the degree of dissociation are represented by the letter alpha. Let us now derive a relation between Van 't Hoff's factor I and the degree of association alpha. The degree of association of a substance, alpha, is defined as the fraction of the total substance that exists in the form of associated molecules. That is, the number of moles associated divided by the total number of moles taken. Consider 1 mole of solute A dissolved in a given amount of solvent. And suppose that n molecules of A associate to form associated molecule AN, and an equilibrium gets established between Na and associated molecule AN. If alpha is the degree of association of the solute, then at equilibrium, 1 minus alpha moles of A are left in unassociated form, while alpha divided by n moles of AN are present in associated form. Therefore, the total number of moles of particles after association is equal to 1 minus alpha plus alpha divided by n. If there is no association, then the number of particles is equal to 1. Substituting the values of the number of particles in the relation, I is equal to total number of moles of particles after association or dissociation divided by the number of moles of particle before association or dissociation. We get I is equal to 1 minus alpha plus alpha divided by n divided by 1. On simplifying for alpha, we get alpha is equal to 1 minus I multiplied by n minus 1. Thus, if the value of n and Van 't Hoff factor I is known, then the degree of association alpha can be calculated. On the same lines, let us now derive a relation between Van 't Hoff's factor I and degree of dissociation alpha. The degree of dissociation of a substance alpha is defined as the fraction of the total substance that undergoes dissociation. That is, alpha is equal to the number of moles dissociated divided by the total number of moles taken. Suppose one molecule of electrolyte A gives n number of ions on complete dissociation. That is, in general, A dissociates to give n1 moles of B plus n2 moles of C plus and so on, such that n1 plus n2 plus and so on is equal to n. If we start with 1 mole of the solute at equilibrium, we have 1 minus alpha moles of the undissociated molecules and n alpha moles of the ions. Thus, the total number of particles present at equilibrium is equal to 1 minus alpha plus n alpha, or 1 plus n minus 1 alpha. Substituting the values of the number of particles in the relation, I is equal to total number of moles of particles after association or dissociation divided by number of moles of particles before association or dissociation. We get I is equal to 1 plus n minus 1 alpha divided by 1. On rearranging, we get alpha is equal to I minus 1 divided by n minus 1. Knowing the value of I from the colligative property measurements, the degree of dissociation alpha can be calculated. Let us now solve a numerical problem based on the association property of a solute. Acetic acid CH3COOH associates in benzene to form a dimer. 1.65 grams of acetic acid, when dissolved in 100 grams of benzene, elevates the boiling point of benzene by 0.36 Kelvin. Calculate Van 't Hoff's factor and also the degree of association of acetic acid. Kb for benzene is 2.57 Kelvin kilogram per mole. The first step is to list the given variables. W2 is equal to 1.65 grams. W1 is equal to 100 grams. Delta Tb is equal to 0.36 Kelvin. Kb for benzene is 2.57 Kelvin kilogram per mole. Molar mass of acetic acid M2 is equal to 60 grams. Van 't Hoff's factor I and degree of association needs to be calculated. Let us first calculate Van 't Hoff's factor I. Substitute these values in the modified equation for elevation in boiling point. Elevation of boiling point delta Tb is equal to I multiplied by Kb multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. On solving for I, we get Van 't Hoff's factor I is equal to 0.5093. Substituting for I in the equation, degree of association alpha is equal to 1 minus I multiplied by n minus 1. Now, n for acetic acid is 2 as it exists as a dimer. On solving, we get degree of association alpha is equal to 0.98. Let us now solve a numerical problem based on the dissociation property of the solute. A solution containing 1.23 grams of calcium nitrate in 10 grams of water boils at 100.97 degrees centigrade. Calculate the degree of dissociation of the salt. Kb for water is 0.52 Kelvin kilogram per mole. The first step is to list the given variables. W2 is equal to 1.23 grams. W1 is equal to 10 grams. Delta Tb is equal to 100.97 degrees centigrade minus 100 degrees centigrade, which is equal to 0.97 degrees centigrade. Kb for water is 0.52 Kelvin kilogram per mole. Molar mass of calcium nitrate, M2, is equal to 164 grams. The degree of dissociation needs to be calculated. For finding the degree of dissociation of the salt, we first need to calculate Van 't Hoff's factor, I. Substitute these values in the modified equation for elevation and boiling point. Elevation of boiling point delta Tb is equal to I multiplied by Kb multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. On solving for I, we get Van 't Hoff's factor, I, is equal to 2.48. Substituting for I in the equation, degree of dissociation alpha is equal to I minus 1 divided by N minus 1. Now, N for calcium nitrate is 3. On solving, we get the degree of dissociation. Alpha is equal to 0.74.